Okay, today we're going to take a look at Newton's method. A quick poll of the classroom here suggests that we may not have seen this last year. Okay, so you'll get an idea of it real quick. This is actually some really good mathematics, very impressive work by Sir Isaac Newton. So let's take a look. Our objectives for the day. Stated objective. Student will apply Newton's method in order to approximate zeros of equations. So obviously we have a lot of different ways for coming up with zeros of equations. We can solve them, we can graph them, we can do all kinds of stuff. Okay, but remember back in the day, they didn't have much graphing and not any graphing calculators for Newton to work with. Okay, so anyway, our language objective, which you don't have to copy for your planners. Student will demonstrate the ability to apply Newton's method in order to execute multiple iterations of a function and determine whether the function converges or diverges. There's some vocabulary in that statement, obviously. We'll get to all of it through the course of the lesson. And your essential question for the day, can I apply Newton's method and approximate zeros? Okay, so let's take a look at how Newton's method works. Okay. For much of this chapter, we have had need to discover the zeros for various functions for various reasons. Obviously, we've said a lot of different functions equal to 0 for different purposes, figuring out what's going on with intercepts and maxes and mins and inflection points and stuff like that. And we have largely depended upon algebraic processes to help us find those zeros. We've used a lot of factoring. We've got the quadratic formula going from time to time, solving for various roots, and so on. Okay, this has been an effective method for us to go about doing it because we have had functions that have been, in most cases, pretty easy to factor, and it hasn't been much of a challenge in order to solve for the zeros. But we've seen a couple of equations along the way where some of the applied problems can get quite difficult to figure out an attack to actually solve the polynomial that we might have going on. Okay, so to help out with this, we're going to learn about Newton's method for approximating zeros. Okay. All right, Newton's method for approximating zeros of a function. Okay, so let's get through the language of this thing. It's one of those typical textbook definitions. Let f of c, our function evaluated at point C, equal 0, where the function is differentiable on an open interval containing the value c. To approximate the value c, we're going to use a series of steps. Okay, so step one in our process, we're going to make an initial estimate of x. We're going to call him x sub 1. As you're going to see, we're going to have a progression whereby x changes step by step. So you'll have x sub 1, x sub 2, and x sub 3, and so on. Okay, and we will estimate the x value that is close to the value that we're looking at. Now, a lot of times problems will actually tell you where they want you to start Newton's method at. So you may not have to make the initial estimate. It may be provided for you. Okay. Sometimes a graph can be helpful, especially if you're still struggling a little bit with visualizing what particular functions might look like in a graph. Having a good mental picture of that graph and understanding that it's trying to cross the x-axis near a particular value, that can assist you quite a bit when picking an initial value for x. Second step, we're going to determine a new approximation for x, okay, by the following equation. Okay, so we start off with x sub 1, and then we'll end up with subsequent values of x at the end of a process. And the process is this guy, x sub whatever step you are on, x sub n. From that, we are going to subtract the ratio of the function evaluated at x sub n, whatever that value is, and then divide that by the derivative of the function evaluated at x sub n. Starting to get a little feedback in the classroom here that we may have seen this before after all. Okay, the third step of the procedure is going to be this, and this is kind of the termination point of the procedure. If the absolute value of the difference between one step and the subsequent step is less than your desired accuracy, then your next step is going to be your final approximation. If that difference is not within the desired tolerances, if you have not arrived at the accuracy that is needed, then you return to step 2 and you run the procedure again. If you are not familiar, okay, this idea of running the same process repetitively is the definition for the term iteration. Okay, so Newton's method is to apply this iteration until the desired results are achieved. Okay, let's look at an example dealing with Newton's method. Calculate 3 iterations of Newton's method to approximate a 0 for f of x equals x squared minus 2. Okay. And this time we're provided with a starting point for our estimations. We're going to begin with an x sub 1 term of positive 1. Okay. Now, if you're looking at the equation itself, you should understand this is a vertically oriented parabola with a y-intercept at -2. So the intersection with the x-axis, you could probably actually determine it for yourself based on your previous knowledge of different functions. But this guy is going to be greater than positive 1, so our x value is going to increase as we look for the approximation, and it will be it'll be not too far. It'll be between 1 and 1.5. We'll look at that here in just a second. Okay, so we have a function, f of x equals x squared minus 2. We need the derivative of the function. Obviously, Newton's method asks us for the derivative in the function, the equation that it has. Okay, so this is an easy derivative, one that we can all agree on, I think. First derivative is 2x. Okay. Newton's method says that each subsequent x term is the result of the current x term minus the function evaluated at the current x term divided by the derivative of the function evaluated at the current x term. Okay, so applying this information for starters looks basically like this: x sub n minus x sub n squared in this case, because our function is x squared, and then from that we have minus 2. And then the denominator, we have our first derivative 2 times x sub n. Okay. Now, opinions vary on what is the best way to go about charting out Newton's method, but there are a lot of different little pieces of information going on. So I actually recommend using a chart very similar to, if not exactly like this, that kind of plots out all of the pieces of information, at least until we get comfortable with all of the information and where it is being installed in Newton's method. Okay, so I've basically just broken all of the terms down kind of individually. The x sub n, there's a column for it. The function evaluated at x sub n, the derivative of the function evaluated at x sub n, and then the 2 ratios that are in the Newton's formula itself. Okay, so here's where we're probably going to need a little bit of calculator help as we move on. Let's just get started. Okay, on the first iteration, where the first row there, n equals 1, the x sub n term, well, we were told where to start. We were told to start at positive 1. Okay, so that's an easy blank to fill in. The function evaluated at x sub n, which is 1. Okay, well, the function evaluated at 1, that's not a challenge either. 1 squared minus 2 is negative 1. The derivative of the function evaluated at positive 1, not a challenge. 2 times 1 is 2. Okay, the ratio of the function divided by its derivative is not challenging either, negative 1/2. And you will find it more convenient using Newton's method to use decimals as opposed to fractions. Not one of the statements I usually make. I usually tend to prefer fractions rather than decimals, but we're going to get an army of decimals here in a minute. And then the final step, take the x sub n term and then subtract the ratio that we just found. Well, you've got a double negative there, 1 minus negative 0.5. So we have a result of Newton's first iteration as 1.5. Okay. Now, what we're going to do is we are going to run the procedure again. This time we begin with the result of the previous iteration. It was 1.5, so we're going to begin with an x sub n of 1.5, and then we're going to do this again. Okay, so now we're starting to get into some values that may be a little bit more or less manageable for us to work with, so we may want to get the calculator involved here. So we need the function evaluated at this new value, so 1.5 squared minus 2. Okay, and we have an value, if I can get back to my lesson, there it is. Okay, 0.25. Oh, that was not what I intended to do. Hold on. And it's going to argue with me here. Let's try it again. A little better there. Okay, so 0.25. Then also we have the derivative of the function evaluated at 1.5. That one's not so difficult to deal with. That is a 3. Okay. The ratio of the two, the function divided by the derivative, we might need a little calculator help on that one if your number sense skills are not so good. Okay, and we have 0.083 repeating. Okay. Now, I don't expect you to cram all these decimal points in. You're going to see we're going to get to some non-repeaters, some irrational stuff here in a minute. Okay, but we need to find a way not to lose these decimal points. When it comes time for us to write down our values, okay, write it down until it begins repeating. That's good enough for the table itself. Let's just try not to lose these values that we have in our calculator, because it can definitely affect what Newton's method is going to do for us here. And now we have the final step down there. Okay, our x sub n is 1.5. From that, we need to subtract the function evaluated at x, which was 0.25, and then that needs to be divided by this previous value that we had, including all of those decimal points that are hanging on there. Okay, so it looks like we are at a negative 1.5, unless I have goofed something up. Let me take a look and see what I've got in my table over here. And obviously I have. What is incorrect here? Okay, my error was just pointed out to me here in the classroom. It was 1.5 minus the result of that 0.083 repeating guy. So I'm not real sure if this is going to match up to my answer in the long run, but we'll see how close we get. So I've got the 1.1417. Okay, so rounded it once it began to start repeating. Okay, so Newton's method, we're going to use it again. So we're using the result of the second iteration to begin our next step. Okay, all right, now here's where things are going to get interesting. We've got that x sub n value. Okay, we're going to need this guy repeatedly. So if I were you, what I would do is I would store my value into the memory of the calculator so that it can be easily recalled. Okay, so I'm going to store this value, and I'm just going to call it, put it on variable a, and then we will go from there. Okay, so now when I need the function evaluated at this variable, all I have to do is hit alpha a, recall that variable, square it, and then subtract 2, just like the function wants, and then I get a result from that calculation. Now let's see if my numbers are matching up. Since I messed this up, 0.06945. Looks like I'm going to lose a decimal point or two, okay, in the long run here. So bear with me if the numbers don't come out exactly right in my file. So let's see what we have. The derivative. So I'm going to go 2a, and I've got 2.83 repeating, which is what I have in my file. Okay. Now I need the function. Okay, evaluated. Now, what you'll learn to do is back when I did a squared minus 2, since I knew I was going to need that value again, it probably would have been smart of me to go ahead and store that value. Okay, but I'm going to need it again, so I'm going to go, okay, I've got a squared minus 2. The result of that needs to be divided by 2a. Okay, and I've got 0.00245 or so. Okay, My file's looking okay right now. And then I need x sub n minus this current value that I have. So I'm just going to go a minus answer. Okay, and I've got 1.41421 and blah, blah, blah. We have an irrational number down there. Okay, so we've just run 3 iterations of Newton's method. So let's see where we stand as far as getting close to the actual zero. Okay, there is the table once more. The last value from Newton's method that was there was that 0.1414216. The actual solution is at the square root of 2, which is 1.414214. After just 3 applications or iterations of Newton's method, we have arrived at basically within 2 millionths of a decimal point of the actual solution. I don't know how that comes across to you, but that tells me Isaac Newton pretty doggone smart. That was a clever way of determining where the roots are for a particular function. Okay, so let's look at another one real quick. Approximate the zeros of f of x equals 2x cubed plus plus x squared minus x plus 1. Continue iterations until 2 consecutive approximations differ by less than 1/10,000th of a decimal. Okay, these are manufacturing type specifications where you need percentage error to be within certain tolerance levels. Okay, so Newton's method can actually provide us with that information about where is an acceptable amount of error and where is not. Okay, so we have a function, 2x cubed plus x squared minus x plus 1. We need the derivative of that function, and very easily we can arrive at that being 6x squared plus 2x minus 1. Okay, Newton's method, the basic structure. Okay, plugging the information in this particular case, which is kind of an intermediate step. You might be able to jump over this step once you get your feet wet here. Okay, but there is the intermediate step that's there, and now we need the function itself. Okay. All right. Now, we're going to need a place to start, and if you look at the graph, somewhere in the ballpark of negative 1.2 is a pretty reasonable guess. It appears to be somewhere near negative 6/5. Okay, so now what we need to do is we need to plug this information in to our function and kind of start working it from there. So let's see if we can't get an idea. So I'm going to go ahead and I'm going to store this negative 1.2 value so I don't have to type it so many times over and over again. Okay, and then I'm basically going to type my equation. I've got 2x cubed plus that a value squared minus the a value plus 1. Okay, and this brings me a value of 0.184, and that's what I have in my file. This value is going to be needed again in future calculations, so I'm going to go ahead and store that as value B. And if you plan on doing this as I am, where you're storing multiple values, it might not be a bad idea for you to label your chart above that top line where you've got everything labeled. Matter of fact, I'll go ahead and do that. Well, I can't do that because when I change the page, it's going to vanish. But you might want to put a B over your f of x sub n. Now the derivative, 6a squared plus 2a minus 1. 5.24, which is what I have in my chart. And I'm going to need that value here in a moment, so I'm going to go ahead and store it as label C. Okay. Now in the fourth column there, we need the function divided by its derivative. Well, that is basically the B value that I've stored divided by the C value that I have stored, and that is 0.03511 and so on. Okay, there it is. And then lastly, we need the initial value, which was A. From that, we need to subtract b divided by c, which is currently sitting as the answer that is in the calculator. So I'm just going to hit answer. And the first iteration of Newton's method yields negative 1.235, blah, blah, blah. Okay. We are getting ready to use this value in order to repeat this process. So I'm going to go ahead and restore my a value. And every time you store over a variable that's previously been saved, it just overwrites it. So don't worry about it trying to combine or anything like that. Okay. So moving on to the next line. Here we go again. Okay. Now, if you're really techno-savvy, you could probably scroll back up since we are not using anything different in our procedure here. If you keep hitting second entry, you will eventually arrive back at your original equation that that we typed in to begin with, and you can save yourself the trouble of typing it over again if that's what you want to do. Okay, so there's the original function being evaluated at a, and now we have a different a value, so it yields a different result. Okay, we want the derivative, so you can type it over again if you want to, or you can scroll back up and you can find it in the memory banks of your calculator. Okay, oops, I put an X in there. The calculator's not going to like that. There we go, change it to A. And we got 5.68 this time. Okay, now we need the function divided by the derivative. 10351, very similar to the previous entry. Uh-oh, did I mess something up? Okay, so I did not take the time to store my new b and c values, so I came up with a value that did not make any sense. Okay, so now let's look at the function divided by its derivative again. Maybe this one will match the chart this time. Yay, that's better. Okay, and now once again we need a minus the ratio of b minus c. I got a question mark on my calculator. That's not an easy thing to do. Confuse the calculator to the point where it just says question mark. And if I haven't made any further mistakes, I got negative 1.23375. So it looks like I'm back on track. Okay, so we are trying to get to the point where the two approximations differ by less than 1/10,000th. And right now we are looking at a approximately 2 thousandths difference between the first step and the second step. So we need to run it again. Okay, so I'm going to save this value as our new a value. Okay, and begin again. Okay, so we got 0.00001. The calculator's jumped over into scientific notation because the value's getting so small. See if I can't remember to store my values this time. And clearly I've hit something incorrect. There we go, got my b value saved. The first derivative at this value. Okay, 5.6653 and so on. Good. I'm going to go ahead and store that as value C once more. Okay, now we need the ratio between the function and its derivative. Okay, getting very small. Okay, I even carried it down to zeros, basically, 0.000002 if we wanted to put a decimal on there. I only took it to 5 decimals. And then finally, we need the initial value minus the answer that is currently being displayed. And I've got a negative 1.233751929 and so on. And the reason we didn't really take it past any decimal points in that, further decimal points in that, because we really only needed to know that 10,000ths place that was in there. And as you can see, the second iteration and the third iteration are now good to the 100,000ths place. So it only took us within 3 steps to get within 1/10,000th of the actual zero. Okay, One final thing to look at, Newton's method has worked because the sequence that we have been using has been converging, meaning it is homing in on a particular location. Newton's method will fail if the sequence is not convergent. Okay, so for example, and I'm going to go through this really quickly without taking time to look at the calculator stuff. We'll just look at the values as they unfold. Okay, try the function f of x equals x to the 1/3 power. We're going to use a starting point of x equaling 0.1. We've got the function. The derivative of x to the 1/3 power is 1/3 of x to the negative 2/3 power. Okay, there is Newton's method, and when we plug in, we've got some complex fraction stuff going on there, and that can be simplified. And basically, the simplification of that complex fraction ends up being 3x sub n. So you've got x sub n minus 3x sub n. So it actually simplifies really nicely down to negative 2 of x sub n. Okay, so let's see this function in action. There are the particulars from the previous slide. Okay, so let's see what we have here. We're just going to start off at negative 0.1. The function evaluated there yields these values, the derivative, the ratio of the function versus its derivative, and then that ratio subtracted from the initial value. We have negative 0.2. Okay, so negative 0.2 is the new x approximation. Okay, so into the function it goes, into the derivative it goes, the function divided by the derivative, and the result of the value minus the ratio. Now you can notice right there, okay, we went from negative 0.2 to positive 0.4. Now that's not really an indicator of anything yet, because those are still very close to the y-axis. So it's very possible those could be it could be a convergent series, and Newton's method is trying to zero in on where the solution is actually at. Okay, so let's try 0.4. Okay, into the function, into the derivative, into the ratio, okay, and then the result. Okay, now we ought to be pretty clear something is up. Okay, we went from negative 0.2, jumped over the x-axis to positive 0.4, which we said wasn't a real big deal, but now we've jumped back across the y-axis, and we're almost to negative 1. This does not appear like it's homing in on anything. It appears to be getting further and further away from itself. Okay, so let's look at it one last time just to eliminate any confusion. Negative 0.8 into the function, into the derivative, the ratio of the function and the derivative, and then the result of Newton's method. And again, we're back across the x-axis, and we're larger than 1.5 now. And basically, we're getting further and further and further away from where it's intended to be at. This is a divergent series. Okay, the magnitude of the gaps between the results of Newton's method, the iterations of Newton's method, is getting larger and larger when it should be getting smaller and smaller. So there is no limit to this problem, is basically what we're saying with a divergent series. Okay, the assignment to accompany Newton's method is going to be on page 229, numbers 1, 2, 8, 9, and 12. Those of you that were absent, I trust you're going to watch your video over this weekend and get that taken care of. We can't afford to fall any more days behind. We've lost too many days here lately, and we do have to get the second half of the Unit 3 test in before the end of the week. So don't count on many work days in class on the upcoming week. Let's get this assignment taken care of and have it ready to turn in at the beginning of class on Monday.